even polynomial functions. All right, but then again, we're using Taylor polynomials to model other types of functions. Why would you use a polynomial to model a polynomial? You already have a polynomial. All right, so I'll put a star on this page because this is sine and cosine. It's basically asking you to do the same thing. We've already looked at sine in terms of the polynomial, but in terms of, you can come up with a series. Now, because honestly, you could never get enough experience. So page 78, deriving the series for sine. This, honestly, I don't know where my brain is sometimes. This is like the most awkwardly phrased question ever. All I really wanted to say is, what's the domain of your series? So I don't know why I went down that particular road, but whatever. So now I told you that on the test tomorrow I'm not going to ask you a specific proof question, but on the final exam there will be a proof question, and it could be one of these. So we're going to go over it now for those of you who will be taking that assessment. All right. And also, again, it gives you a good understanding of where these Taylor and Maclaurin series are coming from. So first we start off with the original function, f of x is equal to the sine of x. F prime of x would be equal to the derivative of that, which is cosine of x. Double prime is negative sine of x. Triple prime is negative cosine of x. The fourth derivative gets us back to sine. All right, so that's where the cycle starts over again. All right. We're looking specifically for Maclaurin. We could come up with a general rule, but it's the Maclaurin ones that end up being the most useful ones, because we could always build off of that. Basically, if you think of the Maclaurin as like a nice blueprint or roadmap to get you to a Taylor series, just by manipulating the x, instead of it being x minus 0, it'd be x minus whatever. That's probably a good way to think about it. What's that? Yeah, literally. So we're finding the derivative of each one of these, or at derivatives, each one of these derivatives at 0. So any instance in which you're taking a sign, the result is always going to be equal to 0. Cosine, it'll be either 1 or negative 1. In this case 1, in this case negative 1. All right. So I'm just going to continue my work in this obnoxious amount of space that I have here for this meaningless question. So sine of x is going to be equal to, now we could do the full-blown expansion, which is to say we have a 0 over 0 factorial times x to the 0th plus 1 over 1 factorial times x to the 1st plus 0 over 2 factorial x to the 2nd minus 1 over 3 factorial x to the 3rd. And really, that's all you need to get you started, because anything that has a sign in it is going to zero out. So we're only left with the 1 over 1 factorial x to the 1st minus 1 over 3 factorial x to the 3rd, And at that point, you have enough to say, okay, it's going to alternate in sign. That's the first thing. And the second thing is that we're only focused on odd values. So I would have 1 over 5 factorial x to the 5th minus 1 over 7 factorial x to the 7th plus meh, meh, meh. And this part is where we actually come up with the rule to represent the entire series. All right? So basically we want to do all this with n's in it. So I need it to alternate. So, and what a lot of people will do is they'll actually just build their summation first, starting with 0 going to infinity, and then worry about the nth term in that same progression. Because really, you do need to have a sense of where you're starting this journey, right? So we know that we can create an odd value by using 2n plus 1. So 2n plus 1 factorial. 2n plus 1 or 2n minus 1, depending on what my starting n value is. All right. Since I want it to start off with a 1, if I go with 2n plus 1, plugging in a 0 for n would make it a 1 factorial. Plugging in a 1, it'll make it a 3 factorial, and so on. All right. I also need to alternate in sign, starting with a positive. All right. So negative 1 to the nth power. All right. 0th power makes it positive. 1st power makes it negative, and so on. So, you know, working our way out from there, you could say, I mean, you might look at it and say, well, maybe I want to have it the exact same powers, but if you do, then everything would be negative. You know, if you made this to the 2n plus 1, then it would only be, like every time you had an odd power, you'd have a negative result, and that wouldn't necessarily be a good thing. Right? Well, it definitely wouldn't be a good thing. Here we're alternating. Anytime you have an even value, which is irrelevant, it would be positive, but we would still have that alternating component when it comes to the words that I just completely lost. I don't know. I was going to say something that was going to be powerful. X to the 2n plus 1. All right, so that's what this nth term would be. So you might even go like this. Put a little question mark there and use this as the way of building it. All right, so that's a way. All right, so anyway, let me. All right, so then the next component of this, and this part, you may not like it, but I got to do it anyway. Because we have the rule, which is good. I mean, we can put that in a little box there. It's nice to have little boxes to really kind of streamline things. That little part there, so basically I just rewrote the series, a slight simplification along the way, but nothing too crazy. The for part, for what? For x belongs to the set of all real numbers, to x belongs to the set of integers, positive integers, what are we up against here? And so that's a big question. And we'll do it this one time, but I will tell you that there isn't really much of a purpose behind having these series expansions unless we could use it for all values of x. All right? We expanded it out infinitely for the purpose of having a polynomial that could model the sine function. If we then restrict it to only existing between, let's say, 0 and 1, then what the hell is the purpose of it? I mean, I'm sure there would be a purpose, but it wouldn't be a very good purpose, right? So what we need to do is determine whether this series converges, right? And so that's the next part of this process. And I'm stealing my own thunder a little bit in that we haven't really talked about power series yet or things like that, but this is the right time to talk about it, so that's what we're going to do. Right? We're dealing with an alternating series, so one thing you could do is apply the alternating series test. All right? But the thing is, I don't want to just know about convergence. I want to know about absolute convergence. Right? So you could even just kind of cut to the chase and say, let me just focus on finding the sum of the absolute value of this, or determining convergence for the sum of the absolute value of this, and not even worry about the alternating series test. Right? Because in all honesty, when you look at the values, I mean, you'd have to have a sense of what X is in order to really get started on it anyway. So I don't really have a sense of the size relationship between numerator and denominator because of that, the presence of the X. But what I can do is start the process of kind of cleaning things up a little bit. And so that's where we're gonna go with this. So first thing I'm gonna do is I'm gonna take the absolute value of it. So, which is basically, it's gonna get rid of the alternating component of it. All right, so I'm looking for absolute convergence. All right. This is a ratio test situation, because we could find the n plus first term. So that's what we're going to do. I mean, it's one of those where it could go either way. You're like, is it the ratio test or the root test? If it's not nth rootable top and bottom, then it's not the root test. All right. So let's apply the ratio test. This would be a sub n. So I need a sub n plus 1. All right. So that's going to give me x to the 2n plus 2. No, 2n plus 3. I'll show the work. 2 times n plus 1, replacing n with n plus 1. So that the presence of that coefficient there makes it a little funkier than that. Right? Because you're going to have a 2n plus 2 plus another 1, so 2n plus 3. All right, so I'm going to clean it up. I'm going to make it x to the 2n times x cubed over. Now this is definitely the weirdest part. This might even be the weirdest question. I want to clean up my a sub n and my a sub n plus 1 because my a sub n, I can make that x to the 2n times x. But on the bottom, I have that 2n plus 1 factorial. All right, so the weirdness comes in evaluating the factorial part because the numerator shouldn't be a problem. And in fact, things are starting to shape up the right way because I have a common x to the 2n. That's beautiful. That's going to make life a lot easier. All right? But this, the factorial, definition of factorial in simple terms is when you multiply by consecutively lower and lower values until you get down to 1. All All right, so in this case, what I'm doing is I'm starting off with 2n plus 3. Then I'm multiplying that by 2n plus 2. That's 1 less than 2n plus 3. Then I would be multiplying by 2n plus 1, 2n, 2n minus 1, 2n minus 2, and so on. But really, I can stop by saying 2n plus 1 factorial. So the moral here is stop your expansion once you get to the common factorial with your a sub n. Once that happens, you'll be able to cancel, and that's where all the magic happens. Limit. Look at that beast.
Who's going to do this?
It's fair game. I mean, this is just the ratio test. So, it's nothing really new. So all the hard parts of this will cancel out now. And even, you could even do something with the x's. X goes into x cubed, x squared times. So this is going to simplify down to the limit as n approaches infinity of x squared over, let me actually make it a little bit nicer. So it's going to give us that. It's crazy.
I like it less now.
What's that?
I like it less now.
Oh, you do? Oh. Well, maybe in a second it'll get better. So, you see that x squared? And you see how the limiting variable is n? When you have a variable that's irrelevant to the limit, it doesn't need to stay within the limit. All right, so this, like the only values that actually have to stay within this limit are the n values. Any other variable can come out. Right? In fact, we're basically treating x like a constant. Constants can come out of limits. Okay, so what this ends up giving us is something very nice. We're going to have x squared times the limit as n approaches infinity of 1 over 2n plus 3 times 2n plus 2. So we're going to get x squared times what? 0. All right, now before you go crazy with this and just say, okay, x squared times 0 is 0, now what does that tell me? We got to think about what causes convergence in the ratio test. What is the condition, like after you do all the work for the ratio test, after you do all the work, how do you know that the series converges?
It's less than 1.
It's less than 1. All right. So what value of x, if any, would allow this to be less than 1.
All.
All of them. All right. So limit will be less than 1 no matter what x is. Therefore, converges for all x by the ratio test. All right. So we get our domain here. X belongs to the set of all real numbers. And again, that's the whole point behind this. I mean, common sense told us that this had to be the case. Otherwise, why are we learning about this to begin with? Yeah. But this is actually the proof for it. One hell of a proof.
So, actually, I have a couple questions. The purpose of the term 2n plus 1, that's to make an odd value?
Correct. Because you're guaranteeing an even number by doubling, and
You add 1.
1 unit away from an even is an odd, always.
So then why in an plus 1, the denominator, are we doubling 2n plus 2?
Oh, because when we're finding a sub n plus 1, we're substituting an n plus 1 in for n.
Oh, okay.
So the operation naturally doubles it.
I see. Also, so this is for sine of x. Does that mean if it was sine squared, that it would be summation squared, or like the
Yep.
things to the right of the summation squared, and then summation symbol on the left of it? Parentheses squared. Got it.
All right, so for cosine, it's the same general structure. Again, the idea is that you're working off of derivatives and plugging it into a rule. But for that one, I don't think I'll bore you with it because it's the same set of derivatives. It's just you're picking up at a different spot. So you're really just shifting one term down the line. So my f prime for sine would be f of x for cosine, and then the cycle would begin with a 1 followed by 0, then -1 followed by 0, and so on. Right? So odds become evens, and away you go. Right? So you can actually, though, practice with this concept of determining absolute convergence for the cosine function, because you should end up being, for any of these Maclaurin series, you should be getting the set of all real numbers, with the exception of functions that don't exist themselves for all real numbers, like a natural log. Natural log itself doesn't exist for the set of all real numbers, so why would the x values, take on negative values as well? Right? So, but I actually already have the answer key up for this. I put the answer key up for the entire unit today, the revised one, so you could take a look at that. But you flip ahead in the path, so I'll just do the one here, and then you'll get the idea. You can manipulate those special cases. You could substitute into the series. You can multiply or divide by a constant and or a variable. Add or subtract two series. Differentiate or integrate a series, and we've already kind of addressed that. Or recognize it as a sum of a geometric power series. But let's just focus on the idea of subbing into a series. So, very simple. You start off with the series expansion, or at least this is the way I like to do it. Because you could sub right into the rule. That's not my favorite way of doing it. Maybe you like doing it that way, I don't know. All right, so we know that it's 1 minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th minus 1 over 7 factorial x to the 7th, and so on. All right, muscle memory at this point because we've tackled this kind of thing a bunch of times already. All right, you're evaluating a function. Now, if you were to substitute into a function, what do? You replace the variable with a number or another expression. Right? Do the same thing here. I'm going to replace the x, every x, with an x squared. So everywhere I see an x, replace with an x squared. And then simplify. Ultimately, you just want to generalize. You want to come up with a rule that can be used to model this expansion. And this is what I was talking about before in saying that I would show you extensively how to come up with this. You know it's going to have a summation. The bounds are negotiable. We generally want it to start off at 0, so we'll make that assumption. All right. I know that I'm going to have odd denominators. All right. I'm gonna pop in a 1 factorial here. Let me just clean it up a smidge. 1 over 1 factorial. All right. So we want to think about how we could represent an odd number based off of this information. So odd numbers, even numbers. If I have a number, and I'm assuming that I'm working in the set of positive integers, so 1, 2, 3, 4, 5. Forget about 0 for a second. If I take a number and I want to guarantee it's going to be an even number, what can I do to it? I can perform an operation on any number and make it an even number. I can square it, not in every case, but in some cases. Simpler. Not divide. Multiply. Multiply by 2, unless that's what you said, in which case I apologize. Yeah, multiply it by 2. Right? Take a number and double it, guarantee it to be even, right? Yeah, I mean, you try any number. Assuming you're starting with an integer value. I mean, you get into fractions, different story, right? So 2n will give you an even number. Actually, multiply by any even number, and you're guaranteed an even number. But the simplest way to do it is to multiply by 2. Now, if through addition or subtraction, I wanted to get from an even number to an odd number, what could I do? Subtract or add 1. So your choices are 2n minus 1, 2n plus 1. All right. So really what you're doing, in order to guarantee an odd number, is you first guarantee an even number because you know an odd number is only 1 unit away from an even number. All right. If you start trying to think about other ways to come up with an odd number, your brain's going to start hurting. But if you think, okay, the number 4, it's 1 unit away from 3, it's 1 unit away from 5. I can get to an odd number by taking 1 step away from 4. I can do the same thing with 6, I can do the same thing with 24. All right? 1 unit away in either direction. So I want to guarantee that my denominator is going to be made up consistently of only odd numbers, but specifically such that they start with the very first one has to be a 1, right? So out of these two possibilities, if I'm assuming my lower bound is 0, if I'm replacing the n with a 0, which one of these expressions is going to give me a 1? 2n plus 1. So we have 2n plus 1 factorial. All right. So you plug in a 0, you get a 1. You plug in a 1, you get a 3. You plug in a 2, you get a 5. You plug in a 3, you get a 7, and so on. So we're good. We got that. All right. We need it to alternate. So that's the next step in the process. So times -1 raised to a power, but my first sign has to be positive. All right. So my first sign has to be positive. So I need this -1 to start off being raised to an even number. So what should it be raised to? Well, n plus 1 would make it raised to an odd number because I'm starting off with 0.
N?
Just n, yeah. Right? Because if I plug in a 0 to start, -1 to the 0th is 1. We're good. Plug in a 1, -1 to the first is a -1. Then a 2, -1 to the second is a +1. Now we have the alternation that we want. All right, so that's the second part of it. Now I need to address the x's. Well, the easy part is just writing the x. Now it's going to be raised to a power. Now, instead of trying to think of a rule that's going to get you 6, 10, 14, and so on, what I would be thinking of is the rule that gets me from my denominator to the exponent. Because in each case, because I doubled the original denominators, the original exponents, the original exponent matched perfectly the denominator. Now the new exponent is twice the value of the denominator. So if I let my denominator be 2n plus 1, then my exponent has to be double that. All right? So 2 times 2n plus 1. So all of that together, I know it's a mess, but all of that together is a rule, and it's Maclaurin. And the way we guarantee it's Maclaurin is that you just have an x. It's not x minus 2, x plus 4, whatever. It's just an x. That makes it Maclaurin. Now, if you want to clean it up further, you can. You could write it as the sum going from n equals 0 to infinity of -1 to the nth over 2n plus 1 factorial times x to the 4n plus 2. That's fine, but that's not a better answer. It's a little neater, I guess. This gets the job done. In fact, I like this one better because this tells me the story of how you came up with each term. Like, I can tell just by looking at this that you had a progression. You're like, all right, let me consider my denominators first, then my alternating signs, then my powers. Here it's like, okay, did you use a rule? Did you just guess? I don't know. You copy out the person next to you. Or divine intervention, that's possible. That could happen too. All right. The step 1 on this one, a little recommendation, because you're looking at e to the x plus e to the negative x all over 2. Start off by thinking of this as 1/2 times e to the x plus e to the negative x. All right, so each one of these has a Maclaurin expansion. Find them, add them together. So add the Maclaurins. And then divide by 2 or multiply every coefficient by 1/2. And then see what pattern emerges and try to come up with a rule for that. All right. If you can handle this stuff, then what I teach you on Monday is not gonna pose any difficulty whatsoever. Another function in a little while. It's just I didn't want to keep it to the basic ones. I wanted to kind of jazz it up a little bit. All right, so we'll talk about power series and go from there. Page 79, we have the Maclaurin series that we're looking for these two types of functions. I gave you a little tip on the last one, but for this, the second one, it's not crazy. What you're going to do is you start off with the known Maclaurin series, which is the cosine of x is equal to son of a gun heck. I'm just looking at my solution to the last problem and it's just killing me. Anybody see the problem there? Power of 3, power of 5, power of 7, this should be x to the first. Ay, ay. So then this should be x squared. I think everything else is probably okay. Let me just double check. Plug in a 0, you get the 2. Yeah, so the rule was fine. It's just when I did the expansion, I missed that part of it. Ay, ay, ay. And the only reason I picked up on it right now is because I was about to write 1 minus 1 over 2 factorial x squared, 1 over 4 factorial x to the 4th, they said the first 4 non-zero terms, absolute values, non-zero, but ideally something that exists anyway. So plus, so 3 mass. We'll worry about the general term all in one shot. So when we're looking for x times the cosine of x, properties of equations, they're still a thing. You multiply one side of an equation by a value, you multiply the other side. So x minus 1 over 2 factorial x cubed plus 1 over 4 factorial x to the 5th, 6 factorial x to the 7th, and so on. All right, so now all I have to do is generalize this. I mean, easier said than done. All I have to do is the hardest part of the problem. But we do have kind of a blueprint. All right, so we're looking at even denominators. So let's create an even denominator. So 2n factorial. If I plug in a 0, I get 0 factorial. Plug in a 1, I get 2 factorial. 2, I get 4 factorial. So we're good. I want it to alternate, positive to negative and back. So negative 1 to the nth power. So we got that too. So we're good there. Right, then negative 1 to the nth, that's easy enough. Right? If you're starting off with 0, if you want it positive first, then it's to the nth. If you want it negative first, it's n plus 1 or n minus 1, generally n plus 1. Right? The thing that has historically jammed people up, and honestly it really shouldn't, is the power part of it. Where it's like, okay, I have to come up with a rule to represent the powers here. And I'm like, no, you know what? Yeah, no. I don't think you do, because don't think of it that way. What you want to do is think about it as, no, I don't have to come up with a rule to represent the powers in in that they're their own expression. Like you're looking at them as odd numbers. So let me come up with a rule for odd numbers. I say no. I'm looking at the relationship between the denominator and the exponent. Consistently, my exponent is one more than my denominator every single time. So you'll come up with the same expression, but with much less thought, right? Because it's like, well, I want it to be one more than my denominator. My denominator is 2n, so make it one more than my denominator, 2n plus 1. And that's it. All right, so we have a Maclaurin series. Now, we could go through the ratio test for something like this, but I personally think it's too similar to the one that we did already. I'd like to do something that's a little juicier. All right, so let's look at the next one. Find a Maclaurin series for h of x equals, find the first 4 non-zero terms and so on. All right, so the little tip here was to find the two separate Maclaurin series and then add them together and divide by 2. All right, so I'm going to write e to the x is equal to 1 plus 1/2, or well, I'll write it. I missed the x. Plus 1 over 2 factorial x squared. You could write the 1/2, but eventually you're going to have to write an expression that involves factorial, so you might as well just leave it. X cubed. I got 4 terms, satisfy the requirement of the problem. But now I have to do the same thing with e to the negative x. Right, e to the negative x is really just telling me to replace every x with the negative x. All right, so if it's raised to an even power, you square or raise a negative to an even power, it's going to remain positive. So it's the odd powers where you're going to have a sign change. So 1 minus x plus 1 over 2 factorial x squared minus 1 over 3 factorial x cubed, and so on. All right, now before you go too crazy and try to come up with a rule for that, you say, well, it's alternating, so let me come up with a rule for that. You don't need to do that yet, because I need to add my Maclaurins first. And once I do that, I'll take stock of the situation, see where I'm at. And then I still have to divide by 2. So e to the x plus e to the negative x. So we'll get a 2. It looks like every odd power is going to cancel out now. Right? They're exact opposites. That's great news. So I'm looking at 1 plus 2 over 2 factorial x squared. I originally started with a function that was entirely positive. I created a function, e to the negative x, that alternated between positive and negative. All of those negatives canceled out something in my original e to the x, leaving me with only positive even powers. So the next one, just using logical reasoning, or I mean, if you want, you can write more terms of the original functions, but it's logical to assume that the next one would be 2 over 4 factorial x to the 4th plus 2 over 6 factorial x to the 6th, and so on. Now, instead of trying to write a rule for this, or even simplifying your factorials and making it some numerical value that may or may not emerge with an obvious pattern, why don't we divide everything by 2 first? Right? Because ultimately we're looking for e to the x plus e to the negative x over 2. So we're looking at now 1 plus 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4th plus 1 over 6 factorial x to the 6th, and so on. So this is something we could come up with a rule for. because we have even factorials, so 2n. Numerator is 1 in each case. It's not alternating, so I don't have to worry about a negative 1 to a power. X to the, even powers, but more importantly, the same even powers as my denominator. So I called my denominator 2n, so my powers would be 2n. Going from 0 to infinity, just do a quick double check. Plug in a 0 for n's, these zap away to a 1. Plug in a 1, I get 2s, 2, I get a 4, 3, I get a 6, so we're in good shape here. All right. So I don't know if you're familiar with hyperbolic functions, but this is actually a way of representing some of those types of functions. So the sinh and cosh stuff that you see in all the formula sheets for Calc, but we never actually do anything with them. This is related to that stuff. There's a whole world of trig out there that doesn't involve the unit circle. It involves the unit hyperbola, which is fascinating stuff. All right, but anyway, we might as well, for something like this, talk about the interval of convergence. All right, so where does this converge? All right, so we have the a sub n. Now, the whole thing is already positive, so I don't have to worry about the absolute value of it. A sub n plus 1, I would get just by, again, replacing the n's with n plus 1s. So x to the 2 times n plus 1 over 2 times n plus 1 factorial, which cleans a little bit, to x to the 2n plus 2 over 2n plus 2 factorial. All right, so just for the sake of a little bit of housekeeping, simplify x to the 2n times x squared. The bottom, as you know, I mean, you don't need me to tell you this, but if you're going to be able to simplify this properly, it's going to have everything to do with the factorials on the bottom and whether you're able to simplify those. All right. So 2n plus 2 factorial, that would be 2n plus 2 times 2n plus 1 times 2n minus 1 and so on. But since I'm looking to cancel out 2n factorial, I would stop at the next one and just call it 2n factorial. Because again, contained within that 2n factorial is everything after, all the way down to 1. It's kind of like if I had 19 factorial and I needed it to cancel out with a 17 factorial. All right, so just something very simple. 19 factorial, and I needed to simplify with a 17 factorial. I would write the 19 factorial as 19 times 18 times 17 factorial over the 17 factorial and cancel them. That's all I'm doing here, just in symbolic form. All right. So you might look at it and say, well, couldn't I just write 17 times 16 times 15 all the way down to 1, top and bottom, and cancel them out individually? Sure, it's a waste of time. Also, when do you stop here? You don't know what the nth term is. So you could write 2n minus 1, 2n minus 2, 2n minus 3, 2n minus 4, 2n minus 5. But eventually you got to get to 2n minus 2n plus 1. Like, you're going to be conceptualizing it one way or another anyway. All right. So the limit as n approaches infinity of x to the 2n times x squared over all that fun stuff, 2n plus 2, 2n plus 1, 2n factorial, over, it's really just x to the 2n over 2n factorial. Alright. That's poor quality and it looks like an H. Didn't really get much better. Alright, so you notice how in some cases here we have an x that's raised to a power that involves an n. If this process is going to work, those have to cancel away. Because the whole reason why we're going to be able to actually complete a problem like this is because we're going to be able to factor out the x's from the limit because the x's won't contain n's. The x will be irrelevant to the limit. If these didn't cancel, you wouldn't be able to do that. And that would be a pretty solid indication that you did something wrong. All right. So we're looking at x squared coming out of the whole thing times the limit as n approaches infinity of 1 over 2n plus 2 times 2n plus 1 and that limit gives me a what? 0 again. So we have x squared times 0. Now they're not always going to be 0, so I just want to make sure we're clear on that. But for the popular Maclaurins, we could expect them to be, because that's the whole point behind them, right? So will converge for all x because regardless of x value, limit will be less than 1 by ratio test. All right, so, that's all stuff that, wasn't directly asked in the question, but it's very important and it's worth getting into because, again, I just go back to that recurring theme of like, why would we learn about this unless it worked for all values of x, all right? So what this tells me is that even something complicated, like e to the x plus e to the negative x over 2, I can represent that with a polynomial function, a series expansion of a polynomial function. And then once I have that, I can do things like find the derivative, find the antiderivative. I mean, really, if you just look at it, this is a power rule situation. If I needed to take the derivative of this, multiply the power by the coefficient, reduce the power by 1. So I'll even just do that off on the side real quick. I'm into like stealing my own thunder for some reason tonight. I don't know why. Well, it'll cut down on the amount of stuff I have to do in a few minutes, so that's good news. So let's say I needed the derivative of e to the x plus e to the negative x over 2. The result is just going to be the sum from n equals 0 to infinity of 2n over 2n factorial, so power multiplied by the coefficient, reduce the power by 1, x to the 2n minus 1. And you could even simplify it a little bit. It would be 1 over 2n minus 1 factorial, x to the 2n minus 1. All right, it actually has the same structure as the original function. So you think about how that might come into play. You know, sorry, can't be on 0. Otherwise we have a domain issue. And that happens. We talked about that last time. The lower bound is going to shift upward, okay? Because it's basically you're transforming the function by taking its derivative. So you're impacting your factorial in the, yeah, because if you plug in a 0 here, you're going to get a -1 factorial, which is meaningless. So it would have to jump up to give you something that's 0 or better. Right, so, just a little application of it. We did some stuff with limits. We did some antiderivatives. Now some derivatives. So, it all comes into play. Now, that being said, again, we're still working with simple functions because the derivative of e to the x is e to the x. So if I did this by hand, I would get 1/2 e to the x plus e to the x times -1, so 1/2 e to the x minus e to the x. All right, so you would still, not technically need this process in order to find something like a derivative, but since this is the foundation of more complicated expressions, that it's kind of building you towards somewhere. Two. And so this is the last thing we're going to do. Page 81, if we need to. But. So the power series, we've explored this, actually. So the idea behind this is that you have some power-related function that's built into your summation. All we have to do is figure out whether or not it will converge, and then under what circumstances it will converge. Right? So it's going to come down to basically just taking note of the situation and deciding what a meaningful approach would be. Right? So we have an alternating series. So we can consider the alternating series test. But then I also noticed that I have powers that are so powers of n. So I might be looking at the root test. Right? So there's a few different avenues that you might consider going down for something like this. All right. So first thing you want to do is consider everything really except for the variable part of it, the part that involves an x. I'm just wondering if maybe I'm starting off with one that's too complicated for you. I don't think it matters. I'm debating. I think it's as good as any. All right, so the idea again is to decide the approach that you want to take. So I'm going to rewrite. So this one starts at 1 and goes to infinity. All right. The reason why it's going to start at 1 is because of the presence of this bad boy right here, that little n at the bottom. If it started at 0, it would be undefined. All right. So that would be bad news. All right. So we're looking at -1 to the n plus 1 over n times 2 to the nth, and then separately x minus 5 to the nth power. All right. So the question again is really ratio test or root test. So since we know that we're dealing with absolute convergence, I can go down that road. So for absolute, what on earth? Hold on a second. Oh, it's a highlighter. Absolute convergence. that gets rid of the alternating part of it. So 1 over n times 2 to the nth times x plus 5 to the n. All right, so I have powers of n, top and bottom. So that's a recipe for the root test. So that's our first move. So try the root test. We prefer the root test because it's easier. It's as simple as that. If that doesn't work, then we'll do the ratio test, knowing that, okay, we wasted maybe a minute as opposed to trying the ratio test when the appropriate method was the root test, and you waste like 15 minutes, right? So try, and that's a good rule of thumb. If you're ever in doubt, try the root test first. It's going to happen quicker, and so if you're wasting your time, you're not wasting a whole heck of a lot of time. All right, so it's going to be the limit as n approaches infinity of the nth root of all this stuff. So 1 over n to the 2n. And really, I mean, I guess I didn't need to separate the x minus 5 to the nth, but I ultimately want to pull it out. So that's my rationale there. But you might disagree. It doesn't matter. One way or the other. So n approaches infinity. All right, nth root for everything. Nth root for everyone. All right, so 1 over n to the 1 over n, that's the weird part, times 2, that's not weird, x minus 5, still in the absolutes. With the idea being that now that the x minus 5 is released from imprisonment, I can pull it out of the whole thing. All right? It's the power of n. It's the merging of x's and n's that kept it trapped within the limit. Once it's freed up from the n's, it can come out. All right. Now this limit is not going to be equal to 0 for two reasons. One reason is because I told you before that they're not always going to be equal to 0, so we had to get to 1 eventually. And the second reason has to do with this bad boy right there, which we're going to talk about in a second, Mike.
Where did the x minus 2 come from?
That's a hell of a question. X minus 2, x minus 2, x minus... Oh, x minus 5. Thank you, thank you. All right, so we know that absolute values, they transcend the limit. So I can pull that absolute value out and make it absolute value of the limit as n approaches infinity of 1 over 2n to the 1 over n. Now, it's up to you, but if you want, you can go calculator on this. The main issue that you're going to run into would be involving the domain. So as long as you set up a window that doesn't involve 0, I think you should be fine. Let me see if I can do that real quick. X to the 1 over x. All right, so let me pause. In my opinion, I mean, you've all had the teachers for which that was not the valid approach, so, take this and run. Oh, my pen. In case you're wondering about how you would go about doing it, if it were not along those lines, I mean, it's not terrible. It just involves L'Hopital's rule. You know, it's the indeterminate form. The n to the 1 over n, that would be something that you'd have to get into the appropriate form so that you could take the derivative top and bottom. All right, so one step in that direction would be to say first a limit as n approached infinity of 1 divided by the limit as n approached infinity of 2n to the 1 over n, but I could take the 2 out and make it n to the 1 over n. All right, so it would be the absolute value of that ratio. At which point I'd be investigating just this guy. All right, so in that case, what I would be doing, and this is where it gets kind of weird, I'd write it as y equals the limit as n approached infinity of n to the 1 over n. And then I would take the natural log of both sides. So I'd have ln of y is equal to the natural log of the limit as n approached infinity of n to the 1 over n. Functions transcend limits, so the natural log can go inside, and I'd be looking at the limit as n approached infinity of the natural log of n to the 1 over n. And so the big question might be, well, why the natural log? And that's because of natural log properties. The power rule for natural logs tells us that the exponent becomes a coefficient. So then I can take that exponent of 1 over n, swing it around and make it the coefficient. And so I'd be looking at the limit as n approached infinity of 1 over n times ln of n. And you say, well, how does that help? Well, if I plug in infinity, I'm going to get an indeterminate answer. It'll be limit as n approached infinity of the natural log of n over n. Plug in the infinity, you're going to get infinity over infinity.
Can you just substitute infinity in at the top when you see like 2n to the 1 over n, and then it's 2n to the 1 over infinity, which is 0, you just cancel it out to 0.
Yeah, but you have infinity to the 1 over infinity, so that's an indeterminate form, so technically it's not something that you can...
You can't cancel right there?
Nah, I mean, you luck out and it works, but you can't always count on it. All right, so at this point, L'Hopital's rule would kick in, and I'd be looking at 1 over n over 1, and I'd find the limit of that as n approached infinity. So that would give me a 0. And then I'd go through the process of backfilling all of this. And so I'd be looking at, interestingly enough, I guess, the natural log of y is equal to this, all of this stuff here was just to give me this. All right, because we took the natural log of both sides. It gave me this conversion, which when I went through the process got me to the L'Hopital form, which essentially got me the 0. So I have ln of y is equal to 0. When I convert over into exponential form, I get y equals e to the 0th power, which is 1. And so at long last, I get the limit of 1, which is 1, over 2 times 1. And so the absolute value of 1/2. All right, so that, oh, I don't need those equal signs. So that's a lot of work. You know, I mean, if you take a stab at it and say, okay, well, it's probably going to be 1/2. You know, I'm sure these cancel out in some way. It'll be fine. Then you get lucky. But instead of doing all this, you go to the calculator, type it in, and just start scrolling. Right? You don't want to. I mean, this is fun stuff to do. It's like, wow, I really know a lot of math. when I do stuff like this, but it's not necessary to get the right answer because ultimately you just need the 1/2. All right, so I have the x minus 5. Bring that back into play here. If I distribute this, I'm going to get the absolute value of x minus 5 over 2. All right. So it's with this that I'm going to determine convergence, because this is the root test. We use the root test to get this far. All right. The root test, in order to converge, limit must be less than 1 for the series to converge. So I'm looking at x minus 5 over 2 as an absolute value has to be less than 1. So I want to clean this up. And this is going to help me to determine the interval of convergence, because this is not one of those situations where it's going to work for all real numbers. Right? This series will only converge under particular circumstances. I want to know what those circumstances are. So what I'm going to do is rewrite it. When you have an absolute inequality, specifically one involving a negative sign, it converts in such a way that the absolute part of it is in between positive or negative, whatever's on the right-hand side. So I have that. I can multiply everything by 2. And then add 5 to everything. All right. So this is almost the interval of convergence. It's very close. The issue is sometimes the bounds, the actual boundaries, can allow for a unique series that also converges just on using a different test. All right, so we also have to test the bounds themselves. But from this, I can get a sense of what the interval is. I know that if I'm more than 3 but less than 7, I'm in pretty good shape. All right, so if I were to graph the original function, if it were ever given to us, and then also graph the series that was given to us, on the interval of 3 to 7, there should be convergence. All right, they should look the same. As you move out of that interval, they should start deviating from each other significantly. All right, so what I have to do, though, is let x equal 3 and x equals 7. I have to test the bounds. For those of you taking this course for the first time, you don't know just how many topics I chopped out of this. This is like the absolute bare minimum of content that needs to be taught in this course. For those of you who are not taking it for the first time, you know I'm telling the truth. So practice your Lamaze somewhere else, I guess. Anyway, -1 to the n plus 1. That doesn't have an x in it, so I don't have to worry about that. N over 2 to the nth, I don't have to worry about that. It's this guy over here. All right, so these values, the x minus 5 to the n, I have to plug in my bounds, 3 and 7, and see what that gives me in terms of a new series, and then test that for convergence. All right, using any of the appropriate tests. It could be alternating series tests. It could be Ratio test, root test. It could be the nth term test. It could be anything you could think of. All right. So we have the alternating component, -1 to the n plus 1. And that's true for both of them, so I'll just jot that down in both cases. Oops. So we have the 2 to the nth, and so I'm going to substitute in a 3 first. So 2 to the nth here, 2 to the nth here. So we're looking at 3 minus 5, this is -2 to the nth. And 7 minus 5 is +2 to the nth. And let me just make sure I'm writing that correctly. I think I am. So I just have to test these two bounds. Now one of them is going to be easier than the other. A lot easier. So we'll tackle the easier one first. All right. When I made my substitution, again, these values here, that's your x minus 5 part. With these x values. So I have -1 to the n plus 1. Now, I guess it doesn't matter which one I start with first. I mean, we're in for a ride no matter what. It's not too long of a ride, but it's going to take a sec. The -2 to the nth. So you'd want to think about what that could possibly be manipulated into, right? And so we could actually break that up into -1 to the nth. It's a little conceptual piece that it makes a big difference. It's just it won't look like it will initially. All right. So this is kind of a weird thing. It's a very rare step that you ever do, but I kind of look at this one as the equivalent of if I were to multiply two radicals, like radical 16 times radical 2. That would be radical 32. You just multiply the things under the radicals. But really what you're doing is you're applying this rule because it's 16 to the 1/2 times 2 to the 1/2. If the powers are the same, you multiply the base of the exponentials. All right? So this is just that in reverse. What it allows me to do is cancel the 2 to the n. So I'll have an n on the bottom, which is not bad. But on the top, this is kind of a nice little thing. If I plug in a 1, I'm looking at an even power, right? So that would be irrelevant. Here I would get an odd power, so that would be a -1. If I plug in a 2, that makes this even and that odd. So either way, I'm going to get a negative, all right? But maybe you don't like that. So you have exponentials. You can keep the base and add the exponents. So -1 to the 2n plus 1. So you could reason it out and say, well, it's always going to be negative no matter what. Or you could just do it this way. But the benefit of reasoning it out is to say, again, I'll just do it very quickly. If I plug in a 1 here, this makes this an even power, so this is positive, making that an odd power, making this negative. So negative product. Plug in a 2, odd power, negative, even power, positive, result negative. Plug in a 3, even power, positive, odd power, negative, product, negative. In every single case, you're getting a negative. So depending on what you come up with here, you could actually save yourself a lot of time and energy, because this is going to be a lot easier to handle than that, right? This, you would have to use ratio test, most likely. What about this one? P-series, yeah. All right, so the first thing I would do, though, is pull out the -1. So that I'm not confused by the presence of that negative there. All right, so then I would just need to know, okay, 1 over n, what's happening there? Well, that would be if it were a limit. In a P-series test, no, it would be conclusive. So it's, you already said it's not going to converge because more than one is converging, so diverging. Diverges by the P-series test. N is equal, P is equal to 1. All right, but that little bit of work made a lot of, made a big difference. If not, I mean, you get into, if you want to do the integral test. Integral test will work. I mean, it's just extra work that you don't want to do, right? But if you clean it up nicely, you can get it into the appropriate form. All right. So the next one, or the next part, the 2 to the nth cancels out cleanly. And so we're left with the sum from n equals 1 to infinity of -1 to the n plus 1 over n. All right. So what I would first do, because I'm looking at an alternating series, if I have a choice in the matter, alternating series test is what I would want to do, because that's very easy to do. So I would be looking to make sure first that it expands to decreasing fractional values. So you'd be looking at 1. They plug in a 1, it's positive. So +1 minus 1/2 plus 1/3 minus 1/4 and so on. So this is alternating and decreasing. So I would find the limit as n approached infinity of 1 over n, which I think, honestly, I think this is probably the most confusing part of the entire unit, is that in the P-series test, we're looking at the sum of 1 over n. And for the alternating series test, we're finding the limit of 1 over n. And they're going to give us opposite conclusions, because the limit as n approaches infinity of 1 over n would be what? 0. So this converges by the alternating series test. All right, so you're looking at two very different outcomes, although your expression is exactly the same. All right, so when x was equal to 7, we got convergence. When x is equal to 3, we got divergence. So I'm going to manipulate my interval of convergence is going to be 3 less than x less than or equal to 7, because 7 is fair game. The length of the interval is 4, right? So the length of interval is 4. center of convergence. Well, once you have the interval itself, the center is very easy because all you're doing is finding the average. It's just going to be 5. And the radius of convergence. You could do that one of 2 ways. If you know the center is 5, you're going out 2 in each direction, or it's just half of whatever the length of the overall interval is. So either way, it's going to be 2. All right, so this is a very, very specific series that works under very, very specific circumstances. All right, so it's not, you know, when you look at it, it's, well, what would I ever use this for? It beats the hell out of me. At this point, it's just a problem that we can reinforce a lot of skills that we learn in class. Because really, if you think about it, I mean, just going back to the top here, we first addressed absolute convergence. We applied the root test. We reviewed some limit concepts. We solved some simple equations or inequalities, and that was fine. And then we reviewed the p-series test and the alternating series test. I mean, in this one question, we basically reviewed the entire unit. Really, if you think about it that way. Like these kind of questions, as terrible as they might seem, you can handle this. You're really, I mean, just by practicing it, you're practicing everything in the unit. You know, so, you know, don't go to sleep on this kind of question. This is a good question. It really gets the skills down. Hey, yeah, you got the extra stuff at the end, the interval and the center of convergence and stuff like that. But it's really this stuff is the heart of that concept. I will tell you that most people, if they screw this kind of question up, it's because they never test the bounds. All right. So on the test, I'll remind you. It'll say be sure to test the bounds, but even if it didn't, you know, it's something that you should have under consideration. Also, I mean, it's open notes, so like when you get to a question like this, you go to this page and say, "Oh, he tested the bounds. I wonder if I should do that also." Yeah. Yeah, packets, any of your handwritten notes. The only thing you can't do is just print up like textbooks and stuff from the internet. You know, so anything that you yourself generated or I gave you in class is fine.
So it'll be 10 questions.
It'll be 10 questions with 1 omit. Yep.